So, is there any questions? I'm asking all the students. Any question, confusion from the first session? I don't see any
Sir,
chat box. Yeah, okay. So I'll clear the screen.
sir, I had a problem. I'm not sure if it's just in mine. In the code that you've sent, Pytorch 101, the visualize sample function is not working, and it's specifically the error that I'm getting is the kernel crashed while executing the code. And I'm not sure if it's in my laptop or something that it's not working. I just wanted to.
I mean, look, I mean, before uploading, I ran it completely on my computer, which it worked, and whatever I showed you, it's like what is existing on my desktop. So you could see all the visualizations, right?
Yeah, I could see. Yes.
Yeah. So if you can figure out after which line the sort of things are crashing, it will be very helpful.
So there's this function that you defined, the visualize samples. Whenever I run that function, I get the same error.
I'm not sure what to do. I mean, because I
I
didn't
guess
had.
others are also having the same problem. They like,
Sorry, others having same problem? Yeah, someone said the code works for. So Megha, thanks for confirming.
okay, so I'll just try myself. Thank you.
So, okay, so it seems for most of you it's working fine. At least if I go by the chat, yeah, it's coming that. So first of all, Aradhana Pandey, you said that for you also the code crashed. So do you know at which line the code crashed? So those who have trouble, can you just speak up?
I guess the problem is not with everyone, so we'll just figure it out on our own. You can continue with the code.
Okay, okay, fine. So first, let me then again, like what I plan to do also is to introduce you with a little bit of PyTorch Lightning. But before that, let me ask you: is the concept of autograd and backpropagation is completely clear to all of you? That's one of the most important concepts which we are going to use. So hello everyone. For someone how the syntax of something required grad function is true and how x dot grad is doing the computation. Is it completely fine? Okay, probability is absolutely fine. So maybe we can just try to go through some other conceptual stuff like activation, like initialization and things like that. Let me so this piece of code is not there in the GitHub. I will upload it, but for the time being we can sort of go through here. Okay, so let me try to share it. Okay, hopefully you can see the window again.
Yes.
Yeah, okay. So sort of in this notebook, what we try to do is try to answer some general questions like how do you optimize your performance of a neural network training, and what are the general principles to keep in mind while you try to set up your training. Okay, so that's the question we are going to answer and see what are the sort of known wisdom, and then take on from there. So here, as usual, like you start something by importing some stuffs. Okay, so let's try to do it. It's like workenv this here. Oh, this, I always made this mistake. Just hang on a second. I get this deprecated stuff. Okay. Okay, good. So sort of we have imported stuff, and whenever maybe in the live coding stuff we have to sort of download some data. Okay, so let's try to do it. So here you can see that we can just copy the device stuff from the this sort of piece I made in a little hurry, so I may need to change something interactively. Good, this is good to go. So we are sort of MPS device and things like that. So we can download the images. That's not so much important. But what is important is that just like in the previous example, let's say you have all this fashion MNIST dataset. I mean, things are getting downloaded. It will get within 10 seconds. The images are there. So we have the fashion MNIST dataset, and we make some train loader, validation loader, test loader. So what we will do, we will use some convolutional network in order to see, like, I won't teach you what is CNN, but rather we will use CNN as a benchmark to sort of demonstrate how to optimize your training stuff. Okay. So here you can see that we are initializing the data loader. So whenever you try to do the data loader, like you already downloaded something in your data set path where things are stored, but now you're forming the data loader with large images, 1024 batch size, which means 1024 number of images will get in one batch, and you can do machine learning on top of that. So this is almost done. Let's wait for a second. Yeah, it will have for the test loader, which is a little bit larger, but that will also be pretty fast. So let it happen, and then we will apply some pre-processing on the images. This is just to bring them sort of on the same footing. So now let's look at this, what we are trying to do. So in the morning, someone asked, how do we automatize, like, creation of multiple layers, hidden layers? So this is, let's say, we sort of want to have, 4 hidden layers. So you see, we just give the latent dimensions of the hidden layer feature spaces, and let's see how we do. So here, first of all, we just, in an empty list, we sort of start appending bunch of nn.linear followed by an activation function. So what happens that you have an empty list. In an empty list, first you're stacking a linear layer followed by an activation function. And this is happening inside a for loop. So first, in an empty list, there is a linear layer activation. When the iteration of the for loop goes to the next iteration, then there is another linear and activation layer. But you see, each time the for loop changes, the layer sizes takes something from these hidden sizes. Okay. So because layer size is like input size plus hidden sizes. So it's sort of different feature dimension, latent dimension of layers you're taking in. And finally, at the end, you have another linear layer. So this is how you, in general, like the base network, you're creating a multi-layered perceptron. The multi-layered perceptron is always like linear activation, so on and so forth. Now you have sort of a list. Okay. Now you can club them, this whole list, inside this function called module list. And whenever you sort of stack this whole list inside a module list, this self.layers becomes a composite layer. It becomes a sequence of nn.modules. And if you do a forward passing, then you see how you do. You give data and input x, you flatten it by this view function, which we discussed in the morning, and you create a for loop iterator on self.layers. So since self.layers is a module list, L will run over all individual layers, and each time you pass the input data x pass to the layer and sort of create an embedded dimension, like embedded feature representation, and you do it over the for loop over all the layers. So once the for loop completes, it's essentially the input data passes sequentially through all possible connected like intermediate layers, and that's the output you have, and you return that data. So what you're doing is that your composite function is built out of many elementary functions, and you're passing your input x, it goes to the first layer, the output of the first layer goes to second layer, so on and so forth, and finally it comes out of the last layer, and when it happens, you return that number. So this is the way you automatize the stuff. So I don't remember the name of the student who asked it, but is this concept clear to you?
Yes, sir, it's clear.
Okay, very good. So now let's try to do that. We sort of again go through identity, the activation functions, and then we sort of try to repeat what we talked about activation functions. So why I'm again going to or trying to repeat the similar concepts, because it's very important how activation functions are clipping the input data, because otherwise if there are jumps, just like you saw in sigmoid, there can be sort of problem in convergence of the training. So let's again go through it. So you have again code snippets to plot the sort of output of the activation functions, which are sitting in after the linear layers. Okay, so let's try to run this code in the. We have the activation functions. So now initializing a network itself is a tricky business. So why do you think it's a tricky business? Look, if you somehow hit a jackpot and can initialize the state of the network, which is almost close to the optimal solution, then your training will converge very fast. But in picture, when you see smooth loss surfaces, it's never the case that the loss surfaces are very smooth. It never happens like that. So you rather want to come up with tricks so that you can be close to the loss surfaces. And how can you do that? So here let's try to sort of understand. So we had an MLP which we call base network, and let's initialize the model. We did it. Okay. Now first what we are trying to do, first we are trying to sort of initialize the weight parameter all by a constant value. Okay, so here is the function for const initialization of a model, that you access the weight parameters and the data you fill with the number C, where that C by default is 0. So here's something you're doing sort of all the numbers 0.05. So you have done it. Okay, and let's see what comes up. Look, so layered. So here what it gives, that for after you sort of initialize, there are different layers. Okay, so all the layers, their weight. So here is the gradient distribution. What is the differential of the output with respect to the weight parameters? And once it passes after the activation function, what are the activated values? So here the activation function, if you remember, was let's go to that activate. Sorry, where was this model? Let me just check back with. Yeah, base networks. So here activation function is whatever you will specify, and when we sort of introduce the model, okay. So activation function was identity, which is it's the identity matrix, no nonlinearity, which was introduced. So it has almost a similar shape after all the layers. Now we want to sort of initialize that. We will initialize the weight parameter as sample from standard normal distribution. So earlier it was a constant value, and then it's from the standard normal distribution, and try to see what happens. So let's do that. And here, now you see the activation distribution. Just let's compare. The activation distribution here were a lot bumpy. And here, you see the activation distribution after the layers are sort of much smoother. So this already gives you an intuition that when you do a weight parameter initialization, whether it's good to initialize the weights as constant value, or whether it's good to sort of introduce them as numbers sampled from a standard normal distribution. So you can see how the distribution of the weight parameters looks like. Okay, and then let's look at the distribution after the activations again. So let's here are the ones. So when you have sampled it from a standard normal distribution, how the parameters are looking after after it's taken from the activation layer, versus let's look at this distribution, the activation distribution when it was initialized as constant values, the identity ones. So this already tells you that just if you want to initialize the weight parameters of a network, like a constant value is never a clever idea. Rather, to get output as smooth as possible, if you initialize from standard normal distribution, they are sort of much smoother. Okay. Now, how will you sort of optimize what are the appropriate initialization values? So here, there is a little math worth going forward through. So here, the assumption is that if you have a linear layer where the output Y is sort of a matrix, like acting on a column vector X. So Y is sum over J, Wi J, Xj. How will we compute the variation of Y? Sort of variation of Y is like these are independent. So, and there is no correlation among individual X. So that's where it becomes like independently identically distributed. Otherwise, there should have been a covariance term, right? Which is not there. So it's a summation over variances, and you can sort of W's and X's are independent. So you can write it as products. And then finally, when you complete the maths, you see that you can compute the variation of the weight parameters as something like 1 over dx, because there is an intrinsic assumption here that the variance is equal for all like dx elements, where dx is the number of the columns here. So what this essentially tells you that if you want to optimize the initializations of the value, you better try to look into like whatever is the variance of the weight parameters. You can estimate it what to initialize, which should go as 1 over the size of the x. It's the dx, the dimension of x, and that you can sort of use as a template value for the initialization. So let's again do this like equal. Now you see that we will, if we have a bias, we will fill the data with 0. Otherwise, we will fill it with standard normal distribution, where we will use this value of 1 by square root of d, because this is the variance. The standard deviation will be 1 by square root of d. So this is the sort of mathematical formula from above which is implemented. And once we do that, you see now all the layer, the weight distribution and activation, like the numbers after it multiplies w times x, and also after it goes through the activation function, sort of has smooth distribution. So this is like a demonstration that whatever is the simple statistical modeling for linear layers is sort of working well, and you have a recipe for the weight initializations of a network. Okay. Now, sort of there are different ways to initialize the weight of a network, like standard practices are Xavier uniform, Glorot uniform. So there are different like uniform random number generator like recipes from which people try to sort of introduce the weight parameters. All of them has like advantages and disadvantages. So one of them, which was Glorot uniform, which is like a normal distribution, but if you have the feature dimensions of x and y, you choose 2 by dx plus dy as the standard deviation. Okay, and there are other uniform distribution where you can sample the weights from the range minus square root of 6 over this to plus square root of 6, where like you can always ask where the square root of 6 comes from, but it's sort of, it comes out of the algebra. Let's put it this way. And there is some blog which is linked, and you are welcome to go through that to get the deviation or derivation of this square root of 6 number. So what we are trying to do is, now we saw that when you initialize the weight parameters of a neural network following standard normal distribution, how the weight parameters and after the activation distributions looks like you need to get them smooth. So we will check them for the Xavier initializations of the weight parameter. So let's try to do it. Let it come. Yeah. So again, you can see that when you sort of use this 0 and 2 by dx plus dy, how things are looking even after the activation distribution. So why I'm telling you this, that these are good way to sort of trace back. Let's say you are not getting good results. Not getting good results in the sense that the result is not optimal or somewhere there is a spike, etc. These are the distributions you can look back for a trained model to check how the shapes of the distributions are looking like and are they good enough. Okay, so that can be sort of a good cross check to build an intuition to debug whether your code is working well or not. Okay, now we will use a particular activation function which is like tan hyperbolic and recheck all these weight initializations. So let's do it. We have initialized the tan hyperbolic optimization, and then like we have called the visualizations of gradients and the activation. So for tan hyperbolic, you can see that here there is some little spike where, although the fitted one, the overall template looks smooth, and after you apply activation functions, it has become smoother. So again, if the weight initialization is following a mathematical modeling, then you can cross-check that across different activation function for sigmoid versus tan hyperbolic, which is performing better. You can easily pick up for sigmoid, there will be more spikes here, and for tan hyperbolic, it's sort of smoother. Okay. So now there are sort of other mathematical modeling of how you should optimize like your weight initialization. Like if the average weight is sort of, if the mean of the weights are 0, then how do you sort of optimize its variance, the distribution of the weights, by initializing the weight parameters. So there are again underlying theories which I'm not trying to go into detail, but this part is sort of easy. Again, if you try to go through, like, if you initialize something where the expectation value of the square is 0, such is the initialization of the weight parameter, then you can figure out that the expectation value of the input x squared distribution should equals to half of the variance of output. And that also, if this kind of weight initializations are done, you get smooth distribution. So this is another third option. So let's try to sort of redo it, that you set the values as 0 mean, and you set the variance as square root of 2 by square root of the parameter shape. So this is coming from this square. So expectation value, like this is where the square root of 2 by square, like standard deviation value is coming from that formula. So let's try doing it. So here you can see again, even when the weights are pretty sharp, okay, just centered around 0, after the activation function, they sort of broadened and have become smooth. So whenever you remember as a thumb rule that there is a bell-shaped curved kind of distribution, neural networks can tackle those weight distribution better, like sort of better for the convergences. Okay, and now let's talk. So first of all, the section for weight initialization is about to finish. So you should get back, like you should get away, you should take away the message that what are the thumb rule to follow when you sort of try to initialize the weights. Okay, it's just the combination of weight initialization and activation. And after that, when you look into the distributions of the weights, if you're not getting good bell-shaped kind of curve, probably they are going to give you trouble later down the line. So keeping this philosophy in mind, you should always try to optimize your weight initialization. So if you have questions, I would like to stop here to take them. Any questions on this context? Nothing? I mean, this is clear what we are trying to do. Okay, no response, so I take it as yes. Now let's try to do that. We have successfully done a weight initialization. So now we want to do some optimization of the whole training. So how we should proceed? Okay, so let's try to do it. So first, there are some snippet of codes which you can go through in your pastime. Like I will upload it in the GitHub. But this is like some training a model, saving it, loading it, things like that. Sorry. So it's not that important. So what do we try to do? That when we are trying to sort of use an optimizer, it's computing the weights following the computation of gradient descent. It tries to compute the loss for like it tries to, for a particular epoch of training, which is labeled as T, and then it tries to compute the gradient of the loss with respect to the weight parameters of a given layer. Okay, and then tries to do backpropagation. So how you should sort of design the optimizers. So here is an optimizer template. So you often remember that the optimizer, when we had, there was a command called zero grad, and then there was a command called backward. So, and there was sort of step. So you should understand that zero grad means it first detaches all the gradients and then set it to zero. So all the stored derivatives are set to zero, and then there is a update parameter. So of course, update parameter rule, which we talked about, it was something like w prime equal to w minus epsilon dot del L del W. Okay, epsilon was the step size. Now you can sort of change this algebraic rule according to your wish. So that should be implemented in the update parameter function. So of course you don't actually use this in your training. For that already there are optimizer inbuilt, but we sort of wanted to understand how it works. So here we will try to sort of understand how this is implemented in the diagram. So this is the default. Eta here is the learning rate and G is the gradient. Okay. So how for stochastic gradient descent it's sort of done. So update rule is p dot grad, and stochastic gradient descent has some momentum parameters called beta 1 and beta 1. Okay. So you sort of try to compute this mathematical rule. So using gradient descent momentum in compute the weight parameters, and now the momentum
Maybe there is some audio noise from your side.
sorry.
Maybe there is some audio noise from your side. Your voice is breaking.
Oh, is it okay now?
Yeah, now it looks fine.
Okay. So look, when you're trying to do loss minimization, then it may be that the state of the neural network gets stuck in a false minima. Okay, so you want to go to the global minima of the loss landscape. If your state of the neural network gets stuck in the false minima, then you probably want to come out of it. And how do you do it? You do it in the following way. First, you introduce a momentum, and the momentum just tries to drive you out of the false vacua and drive you towards the global vacua. So that's why stochastic gradient descent introduces this momentum parameter, beta. Okay, and once you compute using the del L del W, this M parameter, that is like an updated derivative. You can think of the first line as that. And then you use that for the shift of the weight parameters. Okay, so that's how you introduce stochastic gradient descent. So here you can see that the weight update is not done in one step but in two steps, and these two steps are just the mathematical implementation of this stuff. So here p dot grad is this G, okay, and then self dot momentum. So 1 minus self dot momentum star p dot grad, this is the second term, plus self dot momentum beta 1 dot, momentum parameter, which is M, which was stored. So this is iteratively updated, and you compute the weight shift. Okay, so this kind of design of an optimizer itself is sort of a mathematical rigorous stuff, and people have given proposal of different weight update prescriptions when they try to figure out what is the most efficient way to overcome this issue of getting stuck in a local minima. Good. Now the most popular ones are called Adam and Adam W. So why don't we sort of try to see how an Adam optimizer is implemented. Okay, so here we see the mathematical description of atom. So you have the, like, atom has two momentum parameters, beta 1 and beta 2. And then depending on the gradient, you can see what is the implementation of atom. And atom also has this regularizer, which is like epsilon. How it helps that if there is a vanishing gradient, this can be sort of a 0 by 0 issue. So just to avoid that, there is a regularizer in the denominator so that the denominator never vanishes. Okay, and the final weight update happens in these sequences, that you first use the gradient to compute m and the gradient squared to compute phi, and then you use this formula to compute what will be the final weight shift. So just the implementation of atom is this bias corrections and stuff. So the last few lines are essentially implementation of all this formula. So you can just see what, when you look into these optimizers, what sit at the heart of the optimizers. And you can just try a training where you use the same model architecture, but you use different optimizers and try to see how different optimizers help you converging to the global minima, and can sort of evaluate the performance of the optimizers. Okay, so you start with a base model with a ReLU activation and 4 hidden layers, and you also do sort of a weight parameter initialization. Once it's done, you can sort of see what is the accuracy on a like fashion MNIST classification. Okay, and sort of you get the results. Like it's a trained model, so we are not training it anymore, but you sort of get the 90% accuracy with the SGD and with the atom. Okay, good. So do I want to go to more details? Okay, let's go through this part. Now, it's also good to sort of visualize that if you give the same initial state to a neural network model in the space of weight parameters, let's say there are different optimizers which all lead to the same global minima. What is the path they are taking in the parameter space of weights? That's sort of a conceptually interesting stuff. And that's called pathological curvatures. So here, sort of, we try to draw the loss function, compute the loss function for a trained model in the net, like in the spaces of the weight parameters. Okay, and try to draw this curve. So here, first of all, you can see how the sort of loss landscape looks like. Now we want to see, so if you sort of initialize a model somewhere here, it ideally should come to the global minima, but all different optimizers will follow a different trajectory. So we want to sort of visualize that and build an intuition. So let's do it. Okay, we are sort of doing a little training, and we have to do the training because it's while the training is happening, that's when the loss decreases and goes to the global minima. So we sort of, we define the function, and let's try to sort of see how it's going. So here you can see in this two-dimensional path of the weights, if you sort of initialize from the same point, initially all the atom SGD and SGD with momentum follows similar trajectory. Now, if you initialize a momentum parameter to stochastic gradient descent, it is much more stable than the ordinary SGD. Okay, and Adam and SGD with momentum sort of behave similarly with much more stable paths, whereas SGD often gets stuck in a local minima and tries to get away from it, goes completely in a different direction and tries to come back. So that's the phenomena which is shown here, and this is the advantage of introducing a momentum parameter, so that the sort of zigzag fluctuation of the path in the loss landscape is much smaller for SGD with momentum. And you can see, like, defining a right way the atom, how smooth the convergence is. I mean, this is the reason why most of the cases you will see people blindly use Adam or Adam W, because the convergence is much smoother. Okay. And let's, shall I go through this part? Okay. Also, another part is that in the loss landscape, you can have like very sharp region where the derivative itself diverges. Okay. So in that cases, how do you, like, for different optimizers, how do they behave? So here you can see that SGD and like here it sort of shoots off in the weight parameters for the steep optima and it directly falls, whereas something like Adam, it sort of tries to bypass those points with very sharp derivatives, so it has a trajectory and falls towards the bottom. So this is where I sort of want to wrap up the second lecture, that of course all these things you need to go through yourself once more, but I wanted to give you an overall idea that when you choose an optimizer, why you choose it, and why different optimizers behave differently while you do the training. Okay, so hopefully you got a picture that how in the loss landscape the evolution of the network architecture happens when the weight change is happening through different optimizers. And before that, we sort of discuss what is the impact of weight initializations, which we always like, which has a great importance. So these are the two things, at least, like you will have your own model architecture and data set. So you may always try to think of, oh, let's make a neural network very deep and it will solve my problem. No, probably the answer lies somewhere else. Like, first you look into the weight initializations and how the weights are behaving when it's passing the activation functions. Are they smooth enough, or are they well behaved enough? And also what optimizers you're using, because the way the optimizers evolve to take you from some arbitrary state to the global minima, that also has a huge role to play for getting good performance. So like when you will train a model professionally yourself, please keep these topics in mind. Okay, so that's what I wanted to discuss. Yeah, thank you. So if you have questions.
When we take it from local minima to the global minima, how complex does the computation become?
Like it all depends on the shape of the loss surface. Like there can be even degeneracy in local and global minima. So depending on the shape of the loss surface, and first of all, loss surface is defined in like in the spaces of weight parameters. So you can think of that as a hypersurface. If a model has million parameters, that's a hypersurface in the million dimensions. Okay, so it's in general a very complex task. other questions? So if not, then Ritesh, you can probably hand out the exercises to them.
Am I audible?
No, I mean very faint.
Okay. How about now?
Yeah, now it's better.
Okay. No, that I will do. So, does it like conclude your session today?
Yeah. I mean, I have sort of completed what all the basic stuff I wanted to cover.
Okay, perfect.
Hmm.
Not an issue. Okay, so
Can you share this code in the same GitHub link?
Yeah. I will just put this in the same GitHub link.
okay,
So
then I will
yeah,
share the
I
link
will
to the
stop.
quiz.
I will stop the presentation. Okay. Yeah.
Okay. Okay. Can you see the link to the quiz in the chat box? I think it should be right. Okay. Let's say.
It is showing it is no longer accepting a response.
Yeah, it's showing no longer accept.
Okay. Just give me a moment. Just give me a moment. Okay. 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 I will reshare the link. Can you try now? Sorry, maybe it's. Let me share this one. Perfect. It's working, right?
Yes, it's working. I have checked.
Okay, good. So, okay, let's say 10 minutes. I will stop accepting the response on 3:40. Okay, it's not take much. And who like those who submit, I think they can leave for today.
So Amir, do I need to stay or I can leave?
No, it's okay if you can leave.
Okay. Thank you.
Thank you, Sanmay.
Bye.
Yeah.
Bye.
Sorry.
Yeah. Go on. Yeah.
So, is he done, Sanmay?
Yeah, Sanmay is done for today, and the guys are taking their quiz, and I will be closing the quiz on 3:40 by 3:40.
Okay.
If it's done, you may leave. Okay, you guys have like 1 minute left. Okay. Bye bye, everyone. See you tomorrow.